Hey, in this tutorial we're starting off chapter 9 with section 9.2, verifying solutions to a differential equation. Okay, so differential equations contain derivatives. They have an order, so the highest derivative present is our order. So if we had a second derivative, then it's going to be a second order differential equation. We had a third derivative, then it's going to be a order 3 differential equation. They have a degree, and that's the highest degree of the highest derivative. Okay, so for example, if we have a derivative that's cubed, say like we have in our example here in E, which we'll get to, so we have our first derivative that's cubed, okay, well that means that we're going to be a degree 3. Okay, just a little bit of notation that we may not have come across. If we do a x with 2 dots above it, it means that's d squared x on dt squared, or if we had dt squared x, then it's the same as d squared x on dt squared. Okay, so examples of differential equations. So if we had dy dx equals ky, well that's our first order, degree 1 linear differential equation. If we had a times d squared y dx squared plus b dy dx plus cy, okay, that's a second order degree 1 linear equation. For b, we had x double dot take t x dot plus 2x equals t. Well, that's a second order degree 1 linear equation. Okay. Again, with d, if we had d squared y on dx squared plus n squared y equals 0, that's a second order, because it's a second derivative, degree 1 linear equation. For e, we have x outside of dy on dx cubed plus 3 times dy dx plus 5y equals 0. Well, that's our first order, because we only use our first order derivatives. It's degree 3 because it's been cubed and it's non-linear. Okay. We had d cubed t x equals square root of x squared plus 1. Well, that's a third order degree 1 non-linear differential equation. Okay, so really what we're doing in this first section is proving that some of these differential equations work. Now don't be scared off by our proved ones, it's not as bad as what you think, and believe it or not, you've already seen some of these equations in previous sections. You just didn't realise they were called differential equations. Okay, so worked example 1. Verify that the equation y equals x cubed is a solution to the differential equation that we've got here, which is x cubed d squared y on dx squared minus dy dx squared plus 3xy equals 0. Okay, so the idea here is you always work with one side of the equation and make it equal the other side. Obviously, our right hand side is only 0, so we're going to work on our left hand side. Okay, so what we need to do is we need to start by working out our derivatives and second derivatives. So we can say, well, y equals x cubed. Okay, that means dy dx is going to equal 3x squared. That means d squared y on dx squared is going to equal 6x. Okay, really, we've just found all the parts that we actually need, okay, and we can sub all the bits we need into this equation, and it should all equal 0. So we've got x cubed, okay, times by our second derivative, which is 6x, okay, minus our first derivative, which is 3x squared, all squared, okay, plus we've got 3x times y, well we know y is x cubed. Okay, so that means here that we're going to get 6x to the 4, okay, we're going to get minus 9x to the 4, right, plus 3x to the 4, which does in fact equal 0, okay, which equals our right hand side, okay, and we're finished. Okay, so that's all there is for that first worked example. We've got 2 more worked examples we can have a look at. Sorry, we've got worked example 2 here. We've got given that y equals e to the kx is a solution to the differential equation d squared y on dx squared minus 2 times dy dx minus 8y equals 0. Okay, find the value of k where k is an element of all real numbers. Okay, again, we go through the same process. We need up to our second derivative. So we know we've got y equals e to the kx. That means dy dx is equal to k e to the kx. which means d squared y on dx squared, our second derivative, is equal to k squared e to the kx. Sorry, just e to the kx. Okay, so again we've got everything that we need now, so we can put it into our equation here. So we know our second derivative is our k squared e to the kx, okay, minus 2 times our first derivative, which was k e to the kx, okay, minus 8 times y, which is e to the kx, and that has to equal 0. Okay, well, what we can do first is take out e to the kx, okay, as a common factor. Well, that's going to leave us with k squared minus 2k minus 8 equals 0. Well, we can actually have a look at this and go, well, we can go null factor law and say this has to equal 0 or that has to equal 0, but e to the kx cannot equal 0. Okay, think of an exponential graph. I'll put it in here. Okay, it looks like that. Okay, if we change our value of k, it's just a dilation factor. Even if you make it negative, it's not actually going to cross our x-axis at all. Okay, so it can't equal 0 for this. So what we need to do is just worry about this part. So we say, well, our k squared minus 2k minus 8 equals 0. We can actually factorise that to k minus 4 and k plus 2 is equal to 0. Therefore, k equals 4 or k equals negative 2. Okay. Okay, so if we've got that, then we can say, well, y equals e to the kx is a solution to the differential equation. Okay, so I've got one more worked example to go. So it's worked example 3. Okay, we've got to verify that y equals x e to the negative 2x is the solution to d squared y on dx squared plus 4 dy dx plus 4y equals 0. Okay, the only thing that's going to be different with this is if we have a look and we're going to take our derivative here, well, we're actually going to use the product rule. So we can say, well, y equals x e to the negative 2x. Well, let g of x equal x, h of x equal e to the negative 2x. Well, that means that g dash of x is equal to 1, h dash of x is equal to negative 2e to the negative 2x. So that means then dy dx is equal to this times that, plus that times that. So we've got negative 2x e to the negative 2x plus e to the negative 2x. Okay, so that's our first derivative. Now we can make that look a little nicer, okay, by taking e to the negative 2x out. Okay, the reason why this works better is we get then something that's nice to find our second derivative for, because we can do our product rule again. Okay. So this time we can say, well, let u equal e to the negative 2x, let v equal negative 2x plus 1. So then u dash equals negative 2 e to the negative 2x, and v dash equals negative 2. Okay, so when we do that and we bring these together, okay, then we're going to get d squared y on dx squared, okay, equaling minus 2e to the negative 2x, okay, and then we've got minus 2e to the negative 2x times by negative 2x plus 1, okay, which means we can write that a little bit nicer, okay, and we can simplify that down to e to the negative 2x, okay, outside of 4x minus 4. Okay, if we bring our e to the negative 2x out, okay, we can end up with that. Okay, so now we have all our parts. So we have our y, we have our dy dx, and we have our d squared y on dx squared. Okay, our second derivative. So now we can sum it all in and say that we've got e to the negative 2x times 4x minus 4, right, plus 4 lots of our first derivative, which is e to the negative 2x times 2x plus 1, so times negative 2x plus 1, right, plus 4 times our original equation, which is x e to the negative 2x. Okay, so that's what we've got so far. So what we can then do is bring out our e to the negative 2x as a common factor. Okay, when we do that, we're going to be left with our 4x minus 4. Okay, we're going to be left with 4 times our minus 2x plus 1. Okay, and we're going to be left with 4x. Okay, which means we get e to the negative 2x outside of, well, we get 4x minus 4 plus 4 minus 8x plus 4x. Okay, and you can see from that that actually all cancels out. Our 4x and our 4x gives us 8x, minus 8x is 0. Okay, minus 4 plus 4 is 0, so this entire bracket equals 0. 0 times our e to the negative 2x equals 0, okay, which equals our right hand side. Okay, and so we're finished with that worked example. So really, all we're doing in this section is utilising our skills with finding derivatives, okay, and second derivatives, and subbing them into a differential equation, okay, to show that they work. Okay, so hopefully you'll get through these questions without too many dramas.